Hello. This is the first of a three-part series where we are looking at reinforcement learning. This is Answer Everywhere, and we read source code. So in this series, we're taking a look at bsuite, rlax, and flax. These are all from the Google people, the folks at Google and or DeepMind. And I thought it would be fun to learn about reinforcement learning. It seems like a lot of the reinforcement learning stuff is from a few years ago. I think maybe due to the rise of LLMs, the old RL approach isn't as well funded as it was a few years ago. You can see, for example, bsuite is from 2 years ago is the most recent update. It's possible that they have other tags or branches. Well, I guess master is updated more frequently. I don't know if that's intentional. And there is a research paper that goes along with this. So I think that this was, I believe, intended to be an ongoing project, but I don't know if they've just moved their focus elsewhere or what. But I thought this was an interesting enough project to take a look at it. The basic idea is that they describe it as a little bit like unit tests for reinforcement learning algorithms. So they create environments similarly to maybe OpenAI Gym. And these environments are supposed to be quick to run, and they give you useful information about the performance of your reinforcement learning algorithm. And the idea is you have some proposal for a change in your algorithm, and you want to see how that performs and scales before taking the resources to do a full implementation. So that seems like, since this will be bounded intentionally, it may be a good entry point. Let's dig in. This, I believe, is all Python. 56.7% Python, 30% tech. I know they use tech to generate reports. So there should be some LaTeX file for generating a report from a template. Jupyter Notebook is really, we all know, is really just Python. And then the remainder of the tech might be the write-up of the paper. I'm not sure if that's in this repo or not, but we can check. The PyTest is failing. And this is just a graph of some of the stuff they test. So I could pop this out so we don't clip it. So this is a radar graph, I think it's called. And I guess each spoke of this wheel is a continuum from 0 maybe to whatever max is. I don't know if these all are on the same 0 to 1 scale, but I think they may be. Okay, here we go. So 0.25, 0.5, 0.75, which is a little bit weird because the area doesn't scale the same way. And the human eye is kind of like attributing area to this when that may not be actually indicative of how these things are scaling. But you do get a representation of different performance characteristics. So there's basic, which is just like, does your reinforcement learning algorithm do the basic things that they have to do in order for you to call it an algorithm? Scale is how well do you so all of the experiments are resizable. So you might have like a Tetris, I think, of a certain size, and then you might double it and triple it and quadruple it and see how well does the algorithm perform as you increase the scale. And you can imagine why a company like Google would be interested in that. They tend to scale up their big computations like I think maybe AlphaGo is reinforcement learning. Yeah, so they were using convolutional neural networks with 12 layers trained by reinforcement learning. So there is this is Alpha Star mastering the real-time strategy game, StarCraft 2. There's probably some paper here. And so this is by a deep neural network that receives data from the raw game interface. More specifically, the neural network architecture applies a transformer torso. I don't know what a torso is. I think it's different from a torsor to the units combined with a deep LSTM core. So they describe this as similar to relational deep learning, deep reinforcement learning. So I'm going to read all these things later, putting them in Wallabag because my Lector app is not yet ready. However, it's moving along. If you pop over to the Ant Farm channel, you can see me building it. If you like watching code building videos, that's where the code building videos have moved. And I stream there most days, Monday through Thursday. Okay, so and then noise is how robust is it under noise? I think Gaussian noise is what they do, and memory is like how well can your algorithm remember things from the past. So I think LSTM we've talked about. That's a thing that's designed to make sure that memory is good. How well does it generalize? Exploration is there's a sort of a trade-off between having what you might consider a greedier algorithm that tries to make local optimizations versus exploration, where they're trying to learn essentially new tricks, do more explorations of the state space, rather than sticking around the state space that they know well, which is also a decision that I think all humans have to make at some point. Do I stick around where I was born and grew up and strike out somewhere, or do I stay here? That sort of thing. And then credit assignment, I'm not really sure what is up with credit assignment, but I think it's basically when there's a time gap between an action and the reward, how do you assign credit properly? And then they have this as agents. These are essentially different algorithms. DQN, I think, is maybe the basic one. And then we have boot DQN, actor critic RNN, which is RNN is the recurrent neural network, and boot DQN does some bootstrapping. And I think that you can maybe consider that like an adaptive version of DQN. And then you can see that boot DQN seems to dominate, and actor critic seems to be not very good. And then random just does almost nothing. There's a little epsilon ball around random. And so let's dig in. So that may be why this stuff is old. I guess they found a way to do something reinforcement learning like with transformers. I don't know if that's considered a type of reinforcement learning or if it's just similar in spirit or similar in results or whatever. Okay. So we have experiments, environments. So the environments should be more like the OpenAI gym stuff, I believe. Baselines, I'm not sure what that is. Analysis should be for generating reports. And then logging is probably not so fundamental. And then we have a bsuite.py, a sweep.py, and a sweep test. So sweep, I believe, is a sweep over parameters specifically, I think, for scaling. So here's sweep.py. This module exposes the bsuite experiment definitions in terms of bsuite IDs. Each bsuite ID is designed to be a human-readable string in the format environment name /I, where I is the index of the setting in that experiment and that experiments sweep.py file. Each bsuite ID can be used to load an environment via the bsuite.load functions. To iterate over the bsuite IDs for all experiments, use sweep.sweep in all caps. And then you can also iterate over them for a single experiment. For example, sweep.discounting chain. Okay, so I guess we'll start here. This should be a pretty easy entry point. 150 lines of code. For 150 lines, of which I guess 126 are lines of code, is I guess what GitHub is telling me. We're mostly importing experiment stuff. This is, I guess, like the top level sweep file, and we're importing the sweep files of all of the individual things. We have some dicts for settings, sweep, tags, etc., episodes. Parse sweep. This should be for parsing, I assume, the different sweep files. And we're going to split the experiment package name on the dot. Go back 2. I guess the 2 is, what's the format here again? It's /i. So I guess we're getting rid of the slash and the I, although I don't know if the I is only one character. And then we eligible for a sweep test checks if the experiment name ends with ignore for testing. I guess ignore for testing is maybe a some sort of tuple. It says noise or scale. Exclude environment names with the following from the testing sweep. Okay. And then we're constructing bsuite IDs for each setting defined by the experiment. So we're going to iterate over some settings using the Python enumerate thing. And the bsuite ID is going to, we've got separator as a variable, so you can change it. And they're just adding, I guess the separator is a slash, and they're adding the I at the end. Okay, and then they're just defining some like constants that they get from parsing the sweep files. And really, that's about it. There's some maps here. I don't know what these do. There's a tuple of all of the bsuite IDs. A mapping from a tag, for example, memory to experiment. So they're just like filling out this stuff. Okay, so that's the sweeping. And bsuite itself has only a few lines of code. We can look over here in the functions. We've got unpack bsuite ID, load from ID, load and record. Okay, so all of this stuff is really just loading functions from files, and it's the files themselves, the source files that have the reinforcement learning stuff. So we have baselines, which includes jacks, and then random is probably just randomly selecting actions and seeing like as a not quite worst case performance, but like you can't really do worse than expectation than just randomly choosing actions. And then TF, I'm going to guess, is TensorFlow, right? Yeah, probably. And so these are just different implementations of the, I'm not sure what you call it, if it's like the optimization algorithm, DQN, boot DQN, actor critic, and actor critic RNN. And I assume JAX has the same stuff, yeah. So we can maybe compare, I guess these are called different agents. You can maybe compare like what the code of, which one did I pick here? DQN. We can look at the code of the different implementations, TensorFlow versus JAX. TensorFlow is 142 lines. JAX is 159 lines. And I'll just like scroll through it and pass my eyeballs over and see if there's anything that really jumps out to me about the different approaches and syntaxes. There's more casting here. You get like reshaping stuff. I didn't see that as much in Jax. We do have some NumPy stuff. Yeah, okay, we do have it. So I think that among other things, Jax implements like a version of the NumPy API. Hello. Hey, look, you were late. You were not late, Tui. You're right on time. Wait. Where did it go? See if we can get that back by doing this. There we go. That did not work. Right, I'll keep this in the other window then. Other screen, rather. My OBS decided it would start trusting the TLS cert of google.com again. So now I have the chat doc back, but I guess I can't make it force it to be above other windows, at least not at this moment. Okay, so these look about equivalent to me. I don't see, from a code reading perspective, why or whether Jax or TensorFlow is a much better. One is better than the other. They seem about equivalent. I think Jax is newer and faster. Okay, so here's bsuite environments. Cart pole is maybe the smallest one that has some interesting dynamics. Base, I forget what is going on. Bandit should be like just a finite armed bandit. Memory chain, I don't really know. Mountain car. And umbrella chain. And deep sea, I think, is really simple. And so is catch. So let's take a look. So, okay, so we have some state. Cart pole state is a collection named tuple. And I guess the name is cart pole state. I'm not really sure what a named tuple gives you, but you can, I guess, reference it by its name somehow. And its state is x, presumably position, x dot, presumably velocity, theta. Okay, so so this is a car. So I set up my tablet to draw, but I guess I didn't realize that this would be a good stream to draw in. But this is a car that goes left and right on the screen, and it has a, imagine this is the car, and it has a pole like this, and theta is like the direction that the pole is not the direction, but the angle that the pole is, I guess, makes with a cart, and you're trying to keep up this, keep up the pole. This is a classic control theory problem. Inverted pendulum on a cart. So maybe here's a video of it. And I guess this is already stabilized because this person's trying to push it over and it's not pushing over. I don't know if it starts. Yeah, okay. So down here, you start, it's just a pendulum. Nothing is keeping it up. And then he's going to try to keep it up. And I guess it knows now to stabilize because it's been trained. But it's like, balancing. Okay. So that's cart pole. So we need the angle theta. Theta dot is the change in the angle. And then time elapsed. I'm not sure why we need time elapsed. That's not obvious, but I guess it's basically t in the equation. So I guess it is obvious. And then we have a cart pole config, which has the cart's mass, the mass of the pole, the length of the pole, the force mag, and gravity. What is force mag? I don't know. Something about force. So, and then we have a step definition, the cart pole class, and what else do we have at the top level? That's it. Okay, so the cart pole class, so the step is not part of the class. That's a little bit interesting to me. The cart pole class, we'll look at that first. This implements a version of the classic cart pole task. The actions are discrete: left, right, stay. Episodes start with the pole close to upright. Episodes end when the pole falls. The cart falls off the table or the max time is reached. Okay, so there's some height threshold. I'm not sure why we need that. Maybe I don't know. So we have some X threshold, which is a float from 3 to 3. That's maybe the length of the track. We have a time scale, presumably in seconds, so 0.01 of a second, and a max time, which is 10. And then the init range, maybe this is the initial range, 0.05, possibly the angle off of vertical, and then an optional seed. So initially we set it up with all of the state being 0. So I guess 0 is the center of the track. It has no acceleration. Theta is 0, so I suppose we're measuring theta from vertical. Theta has no acceleration, and there's no time elapsed. And then we call this super init function, as we always should. And we get a random seed, passing in the seed, which is initially none, and using the numpy random number generator. And then we have this init function, which is a lambda that's going to, I guess, using the RNG, the random state, we are going to do like uniform sampling from negative 0.01 to positive 0.01 of what? I don't know. I was assuming that was mainly the range of theta, but maybe it's the range of everything. So we have some logging and some reward slash episode logic. So we have some height threshold, which is set the height threshold, X threshold times. So we're just setting these to the stuff that was passed into the constructor. And then we set up the cart pole config with the mass set to 1, the mass of the pole to 0.1, the length to 0.5, force mag is 10, and gravity is positive 9.8. And we have some public attributes, which is the number of episodes, which we get from the sweep. And then we have this reset function, which I think just resets it to the beginning. We set reset next step to false. I guess reset next step is maybe a command to let you know that you can set maybe after the thing is done to say that like the next time step we're going to reset everything. And then the state is just the init stuff. Did we use that before? So so we start here with zeros, and I guess that we're initializing all the variables in this range, if I'm understanding correctly. So maybe this also gets called before the first run. And then we have a step. This step function is going to take an action. And if we're supposed to reset the next step, then we reset ourselves. Otherwise, we call step cart pole, which is the function we haven't looked at yet, passing in the action, the timescale, the state, and the config. And then we compute some rewards. Rewards only when the pole is central, and balanced. So we look at the cosine of the theta and check that it's above the height threshold. So how tall is the pole? The height threshold is 0.8, but I thought the pole was 0.5 in length. So I'm not sure I understand the units here. But at any rate, we're essentially looking at the height and how tall it is, whether it's above the threshold. And then we look at the absolute value of the position and make sure that it's less than the threshold, that I guess maybe we haven't fallen off the track or something. Or I guess maybe central just means no matter how long the track is, we want it to be within 3 and -3 of 0. And then this is, I guess, a Boolean, and we're converting it to 1 if it's true and 0 otherwise. I don't know why you need to do this and not, why not just cast it as a float? I don't know. And what we set raw return, we increment the reward. I guess we're accumulating the reward over, so I guess raw return accumulates the reward over different runs. And the episode return, we're also incrementing the reward. I don't know how episode and raw return are different. And then we look at the time elapsed. And if it's more than max time, or we don't have a reward, then the best episode is set to be the max of the episode return or the current best episode. And then we reset the next time step. And then we look at DM-env, which I think is the DeepMind environment or something. And we call termination with the reward and the observation. Which observation? I don't know. I'm not really sure what's in observation. Otherwise, we call transition with the reward. And _step is not implemented because this environment implements its own auto reset. Similar with some of these. The action spec is a discrete array with 3 values. The 3 values are left, right, and nothing, I guess. And then an observation spec, which has shape 1, 6. So I guess I think that means it's maybe 6 long. And its name is state, and I think they're just observing the state here. Maybe the physics states. Where was that? The cartpole state. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Where the 6 comes in, I'm not sure yet. And then this observation function will produce a NumPy array that starts with all zeros. I guess this is where the 6 comes in. And the state variables are x, the x over the threshold, whether the ratio between x and the threshold, similarly with the ratio of x dot over the threshold, the sine of theta, the cosine of theta. I'm not sure why you need both. The theta dot and the time elapsed over the max time, the fraction of the max time. Okay, so most of that is, I think, understandable. We can look at the step function, step cartpole. So force is equal to action minus 1. So action should be 1, -1 or 0 times the force mag. And then we have cosine and sine of theta. PL is the max, the mass of the pole times its length, I guess the pole length. And then L is the length, I guess, from the config. And then M pole, I forget what length is. At any rate, we're just, these are basically just copying over stuff from the physics. And we compute the physical evolution. So this should basically just be a model of the physics. Temp, this is some temporary variable, I assume, and maybe not temperature. We're going to take force plus the pole mass thingy times the theta dot squared times sine, which is the sine of theta, and divided by m total. M as, I guess, mass. And then we get the theta acceleration and the x acceleration and so on and so forth. Let me fix something here. Or maybe I can't. Okay. All right, so that's fine. We see this, there's like a clear separation of physics. I can't follow what all of these variables are enough to know that I assume that this is the correct physics of what's happening. And then we update the state according to the discrete dynamics. So x is x plus the time scale times x dot. So we've moved in the direction of our derivative. The new x dot is the original x dot plus time scale times the acceleration, where I'm not sure where we compute. Okay, I guess we computed that here. And then theta is the remainder, I guess remainder because we're doing circly things, of, we'll take theta plus the time scale of theta dot, taking the remainder of, I guess, 2 pi. Okay, and so on. All right, so that's cart pole. That seems relatively straightforward. Here's base. And base is basically doing nothing. So reset next step calls time step last. And oh, this is just a base class. This is not actually a base environment, right? Base class. There's a typo for bsuite environments. A bsuite environment is a DMEnv environment with extra metadata. Okay, so this is building on DMEnv, which I think is basically also an abandoned project. DMEnv. Yeah. The DeepMind RL Environment API. Okay. Here is Bandit. A simple diagnostic bandit environment. Observation in a single pixel of 0. Observation is a single pixel of 0. This is an independent arm bandit problem. Rewards are 0, 0.1, up to 1, assigned randomly to 11 arms and deterministic. Okay. So what are we doing? We've got some RNG. The actions is number of actions, which is taken in as a parameter. It is default to 11. And there's some action mask, which is we're going to take a choice of a number in the range of the, I guess, 0 to 11. And the size, I assume, of the sample is the number of actions. And we're sampling without replacement. And then the rewards are, I'm not really sure what lin space is, but they go from, I guess, some sort of linear progression from 0 to 1. I don't know what num actions is, and we're indexing at action mask. So I think intuitively what this is doing is we've got our actions, we've got our samples, and we're just assigning the awards consistent with this. And we set total regret to 0. The optimal return is 1, which I guess in one go, you always select the right one, I guess. And then the number of episodes we get from the sweep file. The get observation is going to call, and we're going to make a 1 thing, a numpy thing of ones, I believe. I don't know what this means. Is this just a 1x1 thing? Let's see. I guess I don't have that. Rlax, I think. Hello, Arjit. How goes it? I had a friend named Arjit. I don't know what he's up to these days. Okay. All right, so let's move on to Rlax. I'm gonna skip OBS. I'm tired of OBS's nonsense. So this should work. Hello. Okay. And before we go into Rlax, I want to know um, if transformers have replaced reinforcement learning. So it's kind of giving me a Weasley answer. It says they can work together. While transformers have made significant strides in various fields, including natural language, natural language processing, and the transformers are a type of neural network that excels at processing sequential data. They've been particularly successful in natural language processing, and they can work together by having transformer-based function approximators. Transformers can be used to represent value functions or policy functions in RL. Okay, so if you need to maybe learn the nonlinear value or policy function, potentially improving the learning process. You can have transformer-based world models. They can be used to model the environment of in RL. And there's hybrid approaches. While there's excitement about the potential of transformers in RL, it's still in active research areas. Okay, I'll say you've misunderstood me. I meant the Transformers toy line and film franchise. So you're wondering. Okay. So draw a picture of a transformer robot program conducting a large-scale reinforcement learning experiment. Okay. Replace the with Optimus Prime. Cool. Make it look more like he's doing reinforcement learning research. I'm actually surprised that it will draw copyrighted images. I mean, of copyrighted characters, or whatever the word is. Whatever the intellectual property thing that covers characters. This is not meeting my expectations, Gemini. All right, back to work. Okay, so let's now take a look at rlax. What's up? This is part 2 of our digging into reinforcement learning. We're taking a look at rlax from Google DeepMind. This is Answer Everywhere, and we look at source code. Okay, so rlax, pronounced relax, is a library built on top of JAX that exposes useful building blocks for implementing reinforcement learning agents. And then we have full documentation at readthedocs.io. You can install it, which is good. And we've got some content. The operations and functions provided are not complete algorithms, but implementations of reinforcement learning specific mathematical operations that are needed when building fully functional agents capable of learning. Values, including both state and action values. Values for nonlinear generalizations of the Bellman equations. Are the Bellman equations linear? Return distributions, aka distributional value functions, general value functions, or for cumulants other than the main reward. I don't know what distributional value functions are. I don't know if this means distribution in the sense of a probability distribution. I doubt it means distributions in the sense of like functionals on function space. And policies via policy gradients in both continuous and discrete action spaces. The library supports both on-policy and off-policy learning, i.e. learning from data sampled from a policy different from the agent's policy. Okay. And then we have a description. There's an agent and he's learned from the environment, and so on and so forth. So first of all, let's look at the Bellman equations. And what is a distributional value function? Any chance this has a Wikipedia entry? No? Is that what it called it? I think that's what it called it, right? Distributional value function factorization. Is that the same sense of distributional value function? Distributional policy gradient? Yeah, I think it probably means a statistical distribution. We propose a distributional policy gradient method based on distributional reinforcement learning and policy gradient. Is this like you get a reward that's a distribution? So I've been trying to figure out how to do that on my own. And if this is a whole field, then I don't have to figure it out, which is a win. No. How about just distributional reinforcement learning? This textbook aims to provide an introduction to the developing field of distributional reinforcement learning at the MIT Press. Preface, Introduction, the distribution of returns. Just get to the point. You don't have to start your book with a story. Just tell me what tell me what this book is about. A hallmark of intelligence is the ability to adapt behavior. Why is it so hard to just find a definition of this, what this field studies? All right, let me just ask the AIs. What is distributional reinforcement learning? That models the entire distribution of possible rewards or returns instead of just the expected value. Okay, that's one sentence. Why why did that book decide not to tell me that? I feel wronged and hurt. No, I don't. Okay. And then whatever DFAC is. Distributional value function factorization. And then, okay, so what is what is a distributional value function? So in the traditional value function, in standard reinforcement learning, the value function V of S, so this is like the Bellman value function, for the action value function Q of SA. So S I think is state, so the action value depends on state, I guess, and the action. Represents the expected cumulative reward or return that an agent can expect to receive from a given state S or state action pair SA. Mathematically, the action value function is defined as Q of SA is the expectation of RT such that RT is equal to S and AT is A, where RT is the cumulative reward received from time T onward. A distributional value function, on the other hand, represents the full probability distribution over the possible returns that an agent might receive from a given state S or a state actor pair. Instead of focusing on the expected value, it returns a richer representation. So it's just yeah, fine. The thing has to have a name, and that's its name. Sounds good. All right. Okay, so that probably complicates the code. I was looking at the Bellman equation. You know, I think I was confusing with the there's some generalization, right? Hamilton, Jacobi, Bellman. A nonlinear, partial differential equation that provides necessary and sufficient conditions for optimality of a control with respect to a loss function. Okay, so I guess the regular old Bellman is maybe linear. Sounds good. Okay, so now let's actually get to the rlax code. And we've got examples and requirements and rlax. I'm guessing requirements is just Python requirements. And in rlax, we have underscore source and some typed stuff. I guess that's probably typing information. And we have a bunch of things like losses, model learning, moving averages, MPO ops, MPO, multi-step, nonlinear Bellman, policy gradients, policy targets, pop art, like that, like this guy. That's Andy Warhol. That's Andy Warhol too. Who's the Liechtenstein? guy, Roy Lichtenstein. Is that what we're dealing with? Transforms, which I think is going to be different from transformers. These are maybe transforms in the sense of functions. Hello, No Goodnix. Good to see you again. And then we have value learning, tree util, vtrace will ignore moving averages, interruptions, general value functions, some stuff about embeddings, some distributions, clipping. I don't know what clipping is, some base class. So I guess I want to start at distributions. So we're importing collections and warnings and checks, but not balances. And distracts. I don't know what those are. I guess those are Python libraries. An array is a checks array. Distracts bijectors. Wow. Distracts is a lightweight library of probability distributions and bijectors. It acts as a JAX native reimplementation of a subset of TensorFlow probability. Okay, so I'm guessing checks is also JAX related. I guess people like the X. Checks is what? A library of utilities for helping to write reliable JAX code. I don't know if these are all Google things or these are just in the ecosystem. Okay, so we have some discrete distributions. And the distribution has sample probs, log prob, entropy, and K1 or KL. I guess like the Kublock, I think Liebler divergence. I don't want to get that person's name wrong. Kolbach. I get callback wrong like 100% of the time. All right, callback Liebler divergence, I assume is what KL is, and then continuous distribution has sample, prob, log, prob, entropy. So this doesn't seem to be any particular distribution. Maybe it's like some sort of ad hoc distribution. You can sample from a set of discrete probabilities, I guess using distracts. This is probably a softmax function. It's got a temperature 1. A softmax distribution. Is there a softmax distribution? So that's the softmax function. Oh, I guess if it integrates through 1, then I guess you can use it as a distribution. Okay. We have the clipped entropy softmax. A softmax distribution with clipped entropy. 1 is equal to not clipping. I don't know what it means to clip the entropy, but that's a thing. So we have a greedy distribution. rlax greedy will be deprecated. Please use distracts greedy instead. I don't know what a greedy distribution is. It seems like greedy is a property of things that evolve over time and not of probability distributions. So this says each state's action pair is updated with a frequency proportional to the frequency it is seen while following the current exploration policy. So maybe a greedy distribution is like the distribution that gives you the greedy behavior or something like that. And then we have epsilon greedy and epsilon greedy distribution and so on. Gaussian diagonal. I have no idea what really any of these are doing. They're calling distracts, and distracts is, I think, the real source of all the behavior here. General value functions, importing checks. We have pixel control rewards, calculates the accumulants for pixel control tasks from observation sequences. The observations are first split in a grid of k by k pixels. For each cell, a distinct pseudo reward is computed as the average absolute change in pixel intensity across all pixels in the cell. The change in intensity is averaged across both pixels and channels. So for example, RGB. So if you have like 5 pixels and 3 channels, then you have 15 pixel slash channels or whatever those are called. And then you should crop these. This seems like something that's starting to feel a little bit like what's the word? Convolution-y. So we're doing some assertions. We've got some observations that we're shaping. Okay, so height and width we get from the 1 and 2. And then calculate the absolute differences across the sequence. We're using J and P to calling its absolute value function, the differences between these observations. Then you average within the shell, the cells to get the cumulants. And I assume that this is some some function that does cell averages using reshape. I don't know NumPy well enough to be able to read. I would have to know at least what the API of reshape is. -1 is maybe going back 1. H is the height. Cell size is the cell size. Then we have the width and the cell size again. And observation shape 3. I don't know. The thing that gives us the averages could be the fact that we give it cell size that we're somehow dividing by the denominator or by the size of the thing. I don't know. We have feature control rewards, calculates cumulants for feature control tasks from a sequence of features. Okay. Interruptions. What is interruptions about? Correct handling of interruptions. So fix step type on interruptions, return step type with the last step before almost every first step. If the environment crashes or is interrupted while a trajectory is being written, the last step can be missing before a first step. We add the last step. Okay, weird. Why is it doing this? I'm not sure. Note that the agent must still then appropriately handle both terminations, for example, a game over in a game, and interruptions, a timeout or reset for system maintenance. Okay, so I guess this is like people on Borg are like interrupting their jobs and they need to they need to resume or something. Okay, so here's value learning. JAX functions for state value and action value learning. They estimate the expected return. So here we're dealing with expectation and not distributions. This is the standard approach. Oops. This is a long file, which is not surprising. It seems pretty central. So the expected return, which is the discount sum of rewards, the discounted sum, probably time discounted, that can be collected by an agent under a given policy behavior. These estimate the expected return. I don't know how that estimation is done. It implements a number of functions for value learning in discrete scalar action spaces. Okay, so there's a TD learning, I guess temporal difference error. And there's a paper citation, Learning to Predict by the Methods of Temporal Differences. I think that's a classic paper. I've heard of it before. So whatever RT is, but we're just adding RT plus the discount of VT. I think RT is maybe the value. R, I think that's a common variable, I think, in the Bellman equation, but I forget what it is. I don't think it's action. Maybe it's the reward. Although I don't know why you would, I don't know. And so we get the target TM1, and then we call JLAX select with stop target gradients. And call the stop gradient on target M1, and then pass in target M1 as the last argument. I have no idea what that does, but that's a thing. Here's TD lambda, the TD lambda temporal difference error. And that's some other paper. And these are all probably all related to different papers. And I think this is like a, not like a, what's the word? Like monster of the week style, just different implementations of different algorithms. So here's Q learning, which I think is a kind of like standard base case sort of thing. See Reinforcement Learning, an Introduction by Sutton and Bardo. I think somebody was telling me in the Discord that they used the Sutton and Bardo book in their class. And this is just like, I guess this is like how to compute the value function, I guess, given standard parameters. Is that what this is? I think that's what this is. Transforms. So these are custom nonlinear transformations. This is a collection of element-wise nonlinear transformations that may be used to transform losses, value estimates, or other multidimensional data. So this is things like sigmoid, logit, hyperbolic arcsine, sine parabolic, power transform, power tx. I don't know what this underscore is doing here. If anything, 1 over p is the inverse of power. Okay. I'm not sure. This looks like we're just raising stuff to a power. Okay, so pop art is what? We have pop art state, which has a shift, a scale, and a second moment, and pop art output, normalized, non-normalized. And I just want to know what pop art is, but I still have no idea. Art, okay, adaptive, rescale targets. Okay, so there's something about adaptively rescaling targets. Why? I don't know. What makes it pop art? Preserves outputs precisely. Okay, so something about rescaling targets and preserve outputs precisely. Learning values across many orders of magnitude. This is some paper from Google DeepMind, and I guess they thought it was cute to call it pop art. Is it supposed to be like Pop Tart? You go. I guess it doesn't want me to read it. Okay, so that's what pop art is. It's something about learning across different scales. I think that maybe the reason you need that is because a lot of this stuff is like scale dependent, as you might expect, because you're doing things like writing down loss functions. And if you have a lot of different scales, then things that are the larger scales may seem like they're more important than the smaller scales, even though that's not that may not be true in the problem that you're modeling. So, for example, if you have some like Bitcoin trading algorithm that makes a few pennies on each trade, then those pennies are in units of small decimals. But you might record some other variable like number of trades, and that's orders of magnitude more than the pennies. But that might not be the most important variable as you're training it. You don't want to really optimize for number of trades. You probably want to optimize for something more like expected value or something along those lines. Okay, so policy targets are utilities to construct and learn from policy targets. I don't really know what a policy target is. It's a data class to hold, possibly sampled, policy targets. And this just has some array, I guess, actions and weights. And maybe the policy is just a list of actions and, how and their weights. Probabilities for corresponding actions. They may have been importance weighted. The shape matches log prob of actions dot shape. The constant policy targets, the actions will be sampled from distribution and will all be associated to constant weight scale. Okay, so I guess maybe the weights are separate from the distribution, and maybe it's like you have some urn, and the urn has some distribution of drawing from it, and then the weights are like you put more balls of one color than the other in, something like that. We have sampled policy distillation loss. Compute a sample a sampled cross-entropy-like loss. The loss corresponds to taking the mean of negative weights times log probability of actions, where the weights and actions come from a policy target object. Okay. What are policy targets? They refer to the desired outputs or objectives that guide the training of a policy. The policy is a function that function or model that maps states or observations to actions determining the behavior of an agent in an environment. So the policy is just the map from actions. Sorry, the map from states to actions. So it's like the transition. It's like the state machine. So is a policy basically a state machine that maps states to actions? Okay. And then we have policy gradients. This is Jack's functions for implementing policy gradient losses. Policy gradient algorithms directly update the policy of an agent based on a stochastic estimate of the direction of steepest ascent in a score function representing the expected return of that policy. Okay, so that, So that means that we're just basically doing gradient ascent. Is that what it says? Steepest ascent. So it doesn't really matter whether we're maximizing or minimizing, but basically we're using the gradient to directly update the policy. And we're just essentially always updating the policy to maximize where the gradient thinks we will go, if I'm understanding correctly. And we've got entropy loss. And it says, you see function optimization using connectionist RL algorithms. Connectionist is not a term that I've heard. I haven't heard that term in many years. What year is this? 2007. This is just the abstract, but I as well read the abstract. We won't do that on here. And then we have QPG loss. Computes the QPG, Q-based policy gradient. See actor critic policy optimization in partially observable multi-agent environments. And I will read that as well. I think I've heard of this paper before. Although we saw in bsuite that at least that their version of actor critic was not very well, didn't perform very well. Okay, here's a nonlinear Bellman. Transformed value functions. We've got two hot pair. Construct a TX pair matching two hot reparameterization and its inverse. Compose TX. Unbiased transform pair. So these look like largely like transformations transformed Q lambda. So this is all consistent with the README of rlax, which said that it's really just a collection of mathematical routines that are mainly used in reinforcement learning. If they were not mainly used in reinforcement learning, there would probably be some other implementation of them. Like if they use them in transformer stuff, it might be in some transformer library. But this is, I guess, the stuff that's unique to this field, that they've gone through all the papers and implemented them and made them available as a library, so that you have a nice experience if you're working in reinforcement learning. I think that now I understand pretty much what's going on here. I don't understand the specifics of most of these things. I think to really understand the specifics, in many cases, you'd have to read the paper. But at least I understand like what the code is about, what it looks like, and when I would use rlax, which is really only if nobody else has with more experience has created a more like batteries included environment for reinforcement learning, because I wouldn't know when to use this loss function versus that loss function without a bit of guidance about like what does the literature say, does my problem look like some other well-known problem, etc., and so on and so forth. We do have we do have losses, so L2 loss. It should be just the L2 norm. If targets are not provided, this function acts as an L2 regularizer for preds. Yeah, look, they're citing Bishop, pattern recognition, and machine learning. That's a classic book. We have likelihood, which takes predictions and targets as arrays, calculates the likelihood of predictions with respect to targets. Pixel control loss, the more pixely stuff. Expectile loss that weighs over/under estimates, etc., etc. Okay, cool. That's the flavor of rlax. I think it's time that we moved on to, what was the last one? Flax. Hello. This is the third in our series of repositories focusing on reinforcement learning, taking a look at Flax from Google. This is not directly related to reinforcement learning, but it is instead related to neural networks. It's a neural network library for JAX, but you might use it in one of your reinforcement learning thingamajiggies if it uses neural networks under the hood. So they're like promoting this NNX thing, which is part of Flax now. I think it used to be a separate repo. Flax was originally started by engineers and researchers within the brain team at Google and Google Research, and is now developed jointly with the open source community. It's a high-performance neural network library and ecosystem designed for flexibility. Okay, I don't know what to expect of this. This might be like rlax in the sense that it's got a bunch of algorithms that are from papers. It might be a little bit more batteries included. Core, linen, I don't know what linen is. Maybe it's something like linting. Core is probably important. OSS, I'm going to guess, is open source stuff. NNX is probably just the API. Metrics, I'm going to ignore. Training is maybe interesting. We have cursor. Why do we need a cursor? IDs, IO, JAX utils, typing information, serialization, struct.py, reverse util, typing inversion. What is struct? Utilities for defining custom classes that can be used with JAX transformations. Okay. The things in the main environment, the main folder seem like utilities. So for training, we have checkpoints, common utils, dynamic scale, early stopping, LR schedule. I'm not sure that I know what LR is. Orbax utils, prefetch iterator, train state. So I'm just a little bit curious about checkpoints and dynamic scale, and maybe early stopping. Let's look at these all quickly. Checkpointing helper functions handles saving and restoring optimizer checkpoints. So this is just for the optimizer. I don't know if we probably somewhere we have to save all of the like configuration stuff. Maybe that's just already in the source file. LR is learning rate. Yeah. Yes. That must be the case. Thank you, No Goodnix. Yeah, I knew it felt somewhere in my mind, but I couldn't get there. I think that I've made this the same thing before. I guess I'm just not familiar with LR being the abbreviation for learning rate. Okay, so is there anything interesting here? So read checkpoint event is a string, and it's set to duration sec, and the write checkpoint event is also a string. Why? I don't know. We've got some regaxes. Regacies? Single group regexes for int or float numerical substrings. Captures sign. That's kind of crazy. Why are we doing this? We have some is multiprocessing array. Are we just gonna like serialize? We have a checkpoint path. Checkpoint path is Orbax checkpoint. I don't know what Orbax is. An async manager to manage async checkpointing. So yeah, you want to do it async so that you're not stopping your training to wait for all the file saves. So you wait for the previous save, and then you submit a new task, which is just some callable, and you set self.save future to be the thing that the future that you get from submitting it. And some stuff for splitting MP arrays. This frankly looks pretty hacky for a Google checkpoint thing, since we're doing regex parsing. But I really don't know. Maybe there's a reason for all of this. You would think that if it's important to save it correctly and get it right, that there would be a more well-defined format, like JSON or protos, where we don't have to do like parsing. But I guess that there's no calls to pickles. I still don't know what orbax is. I'm guessing it's since there's an X, it's Jax related. Orbax is no longer a standalone package. Okay, so the orbax is, I guess, maybe related to checkpointing. Okay, well, whatever. I'm willing to believe that checkpointing is in general hard. Okay, so dynamic scale, I'm guessing is something about scale, and we're dynamically updating it. Dynamic loss scaling for mixed precision gradients. Okay, so mixed precision gradients. I'm guessing that we have within the same gradient, different variables have different precisions. I don't know what else it would mean. For many models, gradient computations in float 16 will result in numerical issues because small or large gradients being flushed to 0/infinity. Yeah. Dynamic loss scaling is an important algorithm. It aims to find the largest scalar multiple for which the gradient does not overflow. This way, the risk of underflow is minimized. The risk of underflow. What about the risk of overflow? I don't see where the asymmetry would. Okay, so the asymmetry is we're looking for the largest scalar multiple for which it does not overflow. Okay. So the value and grad method mimics value and grad beside the loss of and gradients, blah, blah, blah. Okay, so this is something about float 16s. I think we like training in float 16s because it's significantly faster. And I think the downside is the loss of the lack of precision. And I guess this is trying to kind of work around that. JAX cannot execute conditionals efficiently on GPUs. Therefore, we selectively ignore the gradient update using JAX numpy where in case of non-finite gradients. Okay. I'm not going to read this implementation. That's pretty interesting. Maybe a little bit also hacky, but more on the clever side, I guess. You know, often it's not good to be clever, but maybe if this is an optimization that really works in general, then it's well worth it. Okay, so early stopping to avoid overfitting during training. Okay, so this is, I guess this is to detect maybe signs of overfitting, because if it was just about, if you knew ahead of time things that would cause overfitting, you would just train your algorithm less long. So I think this is maybe detecting in real time some known warning signs, some red flags of overtraining. And let's see if that's true. The following example stops training early if the difference between losses recorded in the current epoch, and the previous epoch. I bet both are right. Yeah. I think this is epoch, and this is epic. The first one seems to be epic, so I'll call it that. be recorded in the current epoch and the previous epoch is less than 1 to the negative 3, 10 to the negative 3, consecutively for 2 times. So the difference between the losses is too small. So I guess that's kind of like convergence, right? If the difference in the losses is small. And so I guess it's saying like if we have, is this like if we've converged early, then we shouldn't keep training? Minimum. I don't, is that true? Is this not the same as convergence? Because like, I would think so. If the loss function is no longer, if the loss function isn't moving, has improved, but the metric has improved greater than or equal to the min delta. So the metric is not improving. So maybe it's less, well, it is convergence, but not in the sense of like convergence to something good. Maybe it's just stuck. Maybe it's stuck in some local optimum. Maybe it's stuck in some numerical imprecision thingamajiggy. Our LR scheduling is learning rate schedules, as No Goodnick suggested, used in flax and used in flax image classification examples. Okay. So create constant learning rate schedule. So this is constant learning rate schedule with optional warm up. So I guess as opposed to tuning the learning, I forget how learning rates work, but you can imagine trying to learn faster at the beginning as you're inexperienced, making like larger, bolder steps, and then as you're as you go on, maybe you're pretty sure you're close to some maximum or minimum or what, however they're doing it. You might want to make smaller steps, and so on. We have this is a stepped learning rate schedule. I don't know what flip 1009 is, but this is the second mention. Learning rate schedules and flux training are effectively deprecated. Okay, in favor of optax. So stuff has moved to optax, but at any rate, so the learning rate schedule decreases the learning rate by a specified amount. So this is what I was just talking about, but it's deprecated, so we're not going to look at it. So core has things like axis scan, neural network. That's where I want to be, right? Attention, linear, normalization, and stochastic. I'm guessing these are types of neural networks. I don't know if RNNs are part of it. RNN flip. So we have flax, linen. I guess linen is not about linting. Linen, a comfortable evolution of flax. Linen is a neural network API based on learning from our users and the broader JAX community. Okay. So this is like maybe the second round, but then they're also doing NNX now. Maybe they might be struggling a little bit to get adoption. I'm not sure. I don't know this ecosystem. If you do, please let me know. But so where was so linen had something flax, linen, recurrent, and then was there an NNX version? I'm not sure. Let's look at the linen one. It's long. Recurrent neural network modules. The RNN cell modules can be scanned using lifted transforms. Whatever that means. So an RNN cell base. I don't know what a cell is. Then we have an LSTM cell. Is a cell the same as a network, or is it like a neuron? So what's in a cell? We have a reference to the random number generator, whatever initialized carry is. I guess this. Carry look ahead. I don't know. What is carry in neural networks? Carry refers to the mechanism by which information or states are passed forward through time or layers within the network. This concept is closely tied to how these networks retain and utilize information. In RNNs, the hidden state is the primary form of carry as the network processes a sequence of inputs, for example, words in a sentence or time series data. The hidden state is updated at each time step and carries information from previous steps forward. Okay. So at any rate, it's not implemented. In the LSTM cell, the cell has some call function, so you can call it. It's got a gate function. I don't know if that's how forgetting is implemented, but it's a sigmoid. There's some sort of gating function that's provided by the sigmoid. There's the activation function. I guess this is probably like neuron activation, which is a hyperbolic tangent. A kernel init. I'm not sure what the kernel is up to. A recurrent kernel init. I guess that's different from the regular current. And we have a bias, which I think is like the constant vector term in an affine map. If we're doing, I think maybe we're doing basically a. Are these all linear at the neuron level, or affine at the neuron level, and then you apply a non linear activation function to it, or I guess just some some activation function that gives it a nonlinear behavior. All right. I think that's more or less what's going on. Let's see if there's a diagram. Unfold. So there's before and after LSTM. Bidirectional. I just want equations. RNN come many variants. An RNN function, an RNN is a function f theta of type xt ht goes to yt ht plus a, so it goes up one height level. There's a bias of the presynaptic node. Okay. Yeah, this sigma is a sigmoid. So you take the difference between the y j of the node before it and the bias. That should be essentially the linear map, assuming that I'm understanding bias correctly. So this should be so this difference should be, I think, a linear term. And then sigma is the sigmoid. And we're going to compute that for, I guess, all of the inputs. What are we summing over? 1 to n? I'm guessing maybe n is number of inputs. So for neuron I in the network with activation yi, but I don't know what j is. At any rate, then we have some weights. And then we're going to add the negative of yi, which is, I guess, our activation. And we're adding what's I input, if any, to the node. I think so. No good is saying, I think LSTM is roughly analogous to an attention plus fully connected layer in a transformer. That may be the case, but I don't really know. I frankly don't really know any of this. I haven't read these papers. But I think that's more or less what's going on. How about we just look up neural network instead of recurrent? because a cell of a neural network should be more or less the same as the cell of a recurrent neural network. Try that again. In machine learning. I don't know. What was the first one? The artificial neuron thing? History of perceptron. In the modern sense, a perceptron is an algorithm for learning a binary classifier called a threshold function, a function that maps the input x, a real valued vector, to an output value f of x, a single binary value. So it's binary. So you have some heaviside step function. That's the, I guess, the nonlinearity. And w is a vector of real valued weights. And we're dot producting it with x. This is effectively a linear map. And then bias is the a term. But if we're adding, no, this is the bias is not a vector, as I was thinking about it. At least in this case, the bias is a scalar. Okay. I don't know if that's the case here. At any rate, bias may be a scalar. Not that it matters so much. I read the D2L .ai textbook, and it really helped me a ton. I don't know what D2L is. D2L? Cool. I mean, at some point I will read some of these books, and I'll read some of the papers. I just haven't done it yet. I like to look at the code sometimes before I read the papers because it helps me focus on when you read like an older paper, this is a field that moves fast. So some of these papers, that are written 10 years ago might be considered relatively old or even ancient in this field. And so some of those ideas have really stuck around, and some of those ideas may have been replaced almost immediately. And so it's hard as an outsider when you're looking at a paper like that, knowing which things to prioritize unless you know a little bit about what came later. So it's just it's helpful to kind of have a sort of sense of what people are still considering the really important ideas in retrospect from the stuff that was written back in the day. Okay, so this is some recurrent neural network stuff. Whatever carry is, we have it. This seems to be like a per neuron implementation. And then this whatever dense params, it says it's for some dummy stuff. I'll ignore it. We have an optimized LSTM cell, a more efficient LSTM cell that concatenates state components before matmul. Matmul, I'm guessing, is matrix multiplication. And we have some math. And there's I is the sum over what? I'm guessing I of WII. I'm guessing some sort of weight. I don't know if X, I think X is a variable as opposed to the multiplication sign, plus some WHI weight, I guess. And bias, I don't know if bias is a scalar or a vector, but it's one of those things. All right. And this is a cell. We're still in cells. Somewhere there should be things that are bigger than cells. Or maybe it's all cells all the way. Oops. We have RNN base. Let's look at RNN base. Yeah, I'm sure they have. Okay, so no good at saying bias is vector. Thank you. That's helpful. I learned other language just to read some foreign research paper. Cool. Do you have you also Are you also in the, I guess, like, have you read the machine learning stuff, or do you mean research in other fields? Okay, art and base. This is, we've got an initial carry, some key, some init key, some length, return carry. I don't know if this is supposed to be a cell or what. Anyway, we're going to move on from this linear thing. Now we're back in Flax core. Here's stochastic. I think this is maybe some sort of stochastic neural network. We've got dropout, which applies the dropout mask to the input. I assume that's similar or the same as transformer dropout. So we're kind of like decimating parts of the network in order to not overtrain, to make it maybe more like bagging or training a bunch of related models. I wish the code was more strongly typed and dimensions. It's dimensions, right? Yeah, I agree. We did look at, what was it? We looked at we've looked at a few Python-y projects that try to make typing more strong. And I think that part of the idea of, so some of the, I think Jack stuff might do that under the hood, but it is true that one of the things that's not so fun about Python is you can mix up types in ways you didn't intend to, and the code will just keep running, and your network will probably not train or train super slowly, and you may never know unless you have a lot of tests. So I agree. Although I guess at the end of the day, a lot of the stuff, the type is ultimately like a giant bag of floats in memory. That's kind of the programming model, I think, of NumPy. So I'm not sure, but yeah, you want to have some types so that like as you're reading it, it's clear what this thing is a matrix, this thing is a vector, or in particular, it's like a normalized matrix, or it is orthonormal or something like that. That sort of information is useful. And if you want that experience, you can get it in like theorem provers. That's, in a sense, that's really what theorem provers are about, as the type information allows you to do like reasoning. But it's not. There's no interesting way yet to go like, okay, so I've invented a learning algorithm that has some interesting optimality properties. I've written up the paper. I've like from the paper, I've implemented it in Lean or Coke or one of those other things, and then from there I can extract a JAX implementation. I think that would be a cool workflow. All right, so normalization is normalization modules for Flax, like the batch norm, which I've heard of. I don't really know what it is. The layer norm applies layer normalization on the input. It normalizes the activations of the layer for each given example in a batch independently, rather than across a batch, like batch normalization. Okay, so batch normalization should be, it normalizes larger groups of things. And that's fine. Group norm, I think that's different from the group norm as you might encounter it in group theory. Statistics are shared across equally sized groups of channels and are not shared across batch dimension. Mostly biotech. Cool. That's really interesting. The bio is another field I feel like I don't know anything about. I do know people who are in the field, and so I've seen a little bit of at least the older school methods that they use for like bioinformatics and stuff. I'm sure that that's rapidly changed with AI, things like drug discovery, all of that stuff, and it will change quite rapidly with quantum computing. Since we'll be able to simulate all of the quantum-y stuff going on in the tissues and whatnot. Linear, I'm guessing, is what? Linear models. So are these just like general linear models? You have kernel in it. Again, maybe kernel. So kernel means all sorts of different things. It means the like operating system kernel. It's clearly not that. There's a notion of kernel for some like mathematical operations, like support vector machines have a kernel. But this might be kernel in the sense of the GPU kernel, which frankly didn't occur to me yet because I was trying to think of a mathematical definition of kernel. The compute kernel. Is a routine compiled for high throughput for high throughput accelerators such as graphics processing units and FPGAs. Yeah, so there's all sorts of mathematical definitions of kernel. The pricing kernel is the stochastic discount factor used in mathematical finance. The transition kernel, a generalization of stochastic kernel. The stochastic kernel is a transition function of a stochastic process. So convolution kernel, I don't know which of these it's meaning, but something. Okay, maybe it will tell me. Kernel init. Initializer function for the weight matrix. So I'm guessing that's the linear part of the operation, and I'm guessing that maybe the linear map is just called the kernel. Dense, I'm guessing this is some sort of dense linear something or other, applies a linear transformation to the inputs along the last dimension. I don't know what the last dimension means, but you pass some array and you get a linear thing. The conv is probably a convolution. Applies a convolution to the inputs. Okay, so conv transpose, et cetera, et cetera. Okay, so these are like standard math things, I think. Embedding creates an embedding data class. And we're just, is this embedding thing something we've imported? Or is it just recursively calling the... So we have this struct thing. I guess that's probably what struct was. It's defining this annotation, perhaps. And we have a table, which is a NumPy data array, or ND array, rather, n-dimensional array. Some lookup function embeds the inputs along the last dimension. I don't know what this... I don't know what last dimension is. I'm guessing maybe in the NumPy array. Is that where they are in memory, essentially? And we look at indices and check if they're not one of these floats, or rather ints. And if they're not, then we bail out. Otherwise, we just look up in the table the indices. And maybe the last dimension means that, like, is that what in an ND array? I guess the using the hash table or list indexing notation, maybe indexes into the last dimension, something like that, perhaps. Attend is possibly related to attention. Attend over the embedding using a query array. That sounds related to attention. Query, an array with last dimension equal to the feature depth of the embedding. Returns an array with final dim num embeddings corresponding to the batched inner product of the array of query vectors against each embedding. The batched inner product. Does that just mean we promote one vector to a matrix? Commonly used for weight sharing between embeddings and logic transforms in NLP models. NumPy batch dot product. Suppose I have two vectors and I wish to take their dot product. This is simple. If I have stacks of vectors and I want each one dotted, the most naive code is we're going to call dot for each of these things. It's not obvious to me why we're zipping them. And I want, hang on. Okay, they want all of the like crosswise dot products. Is that what they mean? Okay, so I think this is just like bulk dot product operations, but I think in this case it's a single. There's multiple query vectors. Okay, so I guess the query array is maybe several query vectors. Maybe one for each feature. I don't know. A lot of computing helps, which is getting to your, yeah, that's good. And function X, it may be the function execute on the GPU. I think now that we looked at the comment, I think it's really the weight matrix. That may be the same thing as what's executed on the GPU, but I'm not sure. Here's attention. This is dot product attention. I have read this paper. Computes the dot product attention given query key and value. This is the core function for applying attention based on, this should be attention is all you need. It calculates the attention weights given query and key and combines the values using the attention weights. Okay, so that's, yeah, attention is all you need. That's the standard attention thing, which I'm going to gloss over because we've been here a while. This is the third of the repos we're looking at. Here's multi-head dot product attention. Okay, so we have attention, but I can't remember. I think attention is all you need came before transformers. Oh no, it is the transformer paper. So this is some of this flax stuff is post transformers. It seems like they didn't use, if I'm understanding correctly, I haven't read the paper, but it seems like the StarCraft stuff didn't use reinforcement learning, but used some version of transformers. So I don't know internally at Google what's going on, if there is a migration away from classic RL methods towards something more transformery, or if they're using like a combination of both. But that's not something I know. And I doubt it's something you know. And if you do know it, you're probably not allowed to say. So, but I guess maybe next time I look at machine learning stuff, I might do it after I read some of the like the post transformation papers, because it seems like some of this stuff is I don't know. I don't know how to think about it in the post transformer world. It seems like transformers have taken over and are bringing about the Terminator style rise of the AIs. So I want to make sure that I have a firm grip on that before I spend any time like implementing algorithms that are known to be much significantly outperformed by other stuff that might be even easier to implement because of all of the boom in AI tooling and libraries. All right, so that's all for now. And I have a pretty significant backlog that I had wanted to get up this week, but I will get up next week. And yeah, if you want to see stuff, if you want to see streams where I build stuff, you can head over to the Ant Farm channel. I will add it to the bottom of the video. Thanks for watching.